One.
Okay, whenever you're ready.
Okay.
Okay, we have 10 seconds left. Okay, good afternoon, everyone. Welcome to the crowdsourcing session. My name is Jianan Wang. I'm a professor from SFU. Today, we are going to have 4 really exciting papers about crowdsourcing. And the first paper is from University of Macau. And the speaker will tell you how to use crowdsourcing to answer top K queries. Okay.
Okay. Why? Thanks for the introduction. My name is Naming Ko from University of Macau. This is a joint work with the Nanjing University. Our problem is for the crowdsource top K query. As you may know, crowdsourcing is a strong tool to leverage human intelligence to solve the complex problems. Like here, we have a complex problems. We can split it into a set of microtasks and then distribute the microtasks to the human workers all over the world. This is an example of crowdsourced top K query, which is used by the New York City Mayor Office. The mayor wants to know the top K ideas for creating a greater, greener New York City. And since there are more than 200 ideas, the citizen cannot read all of them. So a common method to do it is split it into the pairwise judgment. So if there are 3 people vote idea A, and 2 people vote B, then we can use the majority voting to decide that A is better. However, how many people we need to ask? In the existing works, most of our work decided this number as a fixed budget. But however, the reality is that difficulty varies. So in this work, we try to decide the budget dynamically due to the difficulty in the running time. But how many microtasks are enough for a pairwise comparison? So how to decide the difficulties? We propose a judgment model to do this task. Here is, we wanted to know who will win the best FIFA men's player, and the UI is here. And instead of only know who is the better players, we also want to know how better it is. So if you think Messi is slightly better, then you can drop the bar to the right-hand side slightly. If you think Ronaldo is much better, you can drop the bar to the left-hand side, to the most left-hand side. Then this preference can be converted into a real value, and we can get a distribution of worker opinions. However, you may know this distribution is just a distribution of samples. It's not the distribution of the overall ideas, right? So we need to use some mathematical tools to get the preference, the average preference of everyone. And given the number of samples n and the quality constraint 1 minus alpha, we can have following equations. And then in the red area is that the average preference can fall into this area with high probability. In the beginning, this average preference can fall into left-hand side of the 0, where 0 is the natural point. The natural point means that these two players are exactly the same. And there are some probability that this preference can fall into the left-hand side and the right-hand side of the natural point. That means we cannot conclude which one is better with high probability. And with more and more players, we can finally conclude that Messi is better than Ronaldo for everyone with high probability. But when we have this judgment model, how can we find the top K list? Before we introduce our methods, we first give some observations. This observation is that, let's think about that. What is the infimum cost of this problem? The key observation is, it is hard to judge two items if they are near in the total order. So we have a set of items, O1 to ON in total order. And comparing O2 and O3 is much harder than comparing ON and O3, because they are more difficult. So we need to avoid comparing the near items. This is the key observation. Then we give our first lemma. Given a set of items, the infimum cost to find the top K list is, first, we put the non-result items by the case item. And then we compare the remaining items with their neighbors, and luckily find that they are already sorted. So the total cost is just n minus 1 comparisons, a linear cost. And we prove that any algorithm cannot achieve a lower cost. So this infimum cost gives some key ideas to develop this method. We propose a select partition rank framework for this problem. In the select session, what we want to do is find the case item. But actually, it is almost impossible to find the K, right? If we can find the K easily, we can just find the top K. So we need to do some trade-off. We want to find a good reference, which is slightly behind the case items. And these items has similar pruning powers. How to find this, find this good reference? The intuition is that, consider we do the max query on a sample set. A set with one sample, then this sample is uniformly distributed on the item space. Then the expected position is n over 2. And For a set with n samples, then all these items are sampled in the sample set. Then the max one is already the first items. So there is something in between. The lemma 2 tells us that there exists a pair of integer x and n such that we first sample a set of x items and then sample another x items until we get m sets. And then we do the max query on each set. Finally, we get a set of max items. Then we select the median as the reference. It is a good reference with high probability. Now we have a good reference. We want to use this good reference to compare with all the items in the item space. And then the items can be split into two sets. One winner set and one is the loser set. And this can be done in parallel. So in each round, we ask one more microtask for every non-distinguished pair is outsourced in parallel. And then almost all the items will be classified into these two classes. But since we need to control the budget, we may stop this partitioning if the remaining pairs cannot be distinguished in the B microtasks. So we call these items a tie case. This tie case means we think they are actually similar to the reference, totally equivalent in our problems. So we can return any one of them. Last, when we get these candidates, we have another key observation is that as we already compare all the items with the reference, in the comparison, if OI is much better than the reference, while the other item, OJ, is slightly better than the reference, then there is a high chance that OI is much better than OJ. So use this observation, we can sort the candidates without outsourcing any microtasks. So this is offline. And then we can get a near sorted list. And then we can use the best case sorting algorithm to find the top k items. The cost analysis is here. The infimum is we want to achieve. And our method is SPR. And the difference is the extra cost. For the selection phase, we know that the infimum luckily pick the case items, so there's no cost. But we need n comparisons, which is controlled. The details in our paper. We want to control the total cost of the selection phase, and then we can do it in the n comparisons. In the partition phase, that the infimum cost is n minus k comparison. So just put the non-result items by the case item, and our method need to compare the reference with all the items. And the difference is k-1 comparisons. And the rank seems we get near sorted the list, so the difference is nearly none. So we get this. Our method is up to is near 2 times to the infimum cost. So this is not a very big gap. Now we talk about the experiments. There are 2 sets of experiments. One is for the non-confidence aware methods. So the most of the related work are in this category. And you can find all of them in a recent survey last year. And another set is the confidence aware methods. So there's only one method remain, ICML previous years. But these methods assume that there is no transitivity in this space. So if A is better than B, B is better than C, C may better than A. So circle may remain. But this is not, in the practice, this is not a very usual assumption. And the other methods are the heap sort, tolerant tree, and quick select. This is the fashion framework for all these top K query algorithms. And our algorithm select partition rank, SPR. The setting is here. We have 4 data sets. The first for the movie, for the book, for the joke, and for the photo. And only the photo data set is collected by ourselves. So it is naturally the pairwise comparison. For the other data sets, they are rating data set in the source. So we transfer the rating into pairwise comparison. And the results show that SPR has the lowest cost according to the number of microtasks. And PBR seems it thinks the transitivity is not exist. The cost is highest. We also show the effect of K that I want to tell the audience is that I want to show that our method, the square one, is very near to the infimum cost one. So the lowest one. And it's very similar to our analysis, is 2 times cost. And this is a performance summary in a 2-dimensional space for the latency and the cost. SPR is the only one can achieve near the infimum cost one. And for the non-confidence aware methods, we only compare to the CrowdBT and hybrid. This is 2 methods recommended by the experimental survey. And seems hybrid employs a grading UI, filling the non-result items in the first place. So the UI is different. So we combine this UI in our methods to propose a hybrid SPR. The results show that with the same cost, in the movie data set, SPR and the hybrid SPR are the best methods. So the result quality is highest. And in the book data set, that in some cases, hybrid is better. This is because the grading performs well when the items are easy to distinguish. Finally, I conclude my talk is that in this work, we dynamically design the pairwise budget according to the comparison difficulty. And with this dynamic budget, we propose a select partition rank framework to achieve the infimum cost. And in the future, we will further investigate the impact of different user interface and how to integrate prior knowledge into this process. Thank you so much.
Any questions?
Well, thank you for your talk and very nice slides. So I have a question about, so for example, you use only pairwise comparison as your cross-sourcing tasks, yeah. And how many workers will you retrieve for each task? And also it sounds like you treat each worker as identical. That is, you do not distinguish different workers, and maybe some are spammers and some are experts. Yeah. And to aggregate their answers, you just regard them as identical. So is there any possible chances that you can incorporate or model differently in the workers?
Yes, good question. In this work, we only consider how to doing this process to achieve the infimum cost, and we ignore the worker quality. But I think it is, of course, possible to integrate all the work for the worker quality into our framework. Yeah.
Any other questions?
Thank you. Sorry, I missed the beginning of the talk. So I want to ask, what's your assumption of the crowdsourced answer? Do you assume, for example, the true answer for a question is 0 or 1, and the crowdsourced answer follows some kind of distribution, like binomial distribution from the true answer?
Yeah. So your question is about the distribution of the input, right? I get it. In this work, as I have shown in the previous slides, we assume that the input is under the normal distribution. However, we are doing an extension for this paper that is no any distribution assumptions. So for any distribution. Yeah, thank you so much.
Any other question? Okay.
In fact, I have another question. Given that you have 3 phases, do you give some guidelines for the requester? For example, I give you $10. How can you distribute this $10 into different phases? Do you give some guidelines?
Yeah. We use half of the budget in the first phase and the others for the second and third phase. Because of the second and third phase, the number of comparison is almost decided. Yeah, it's near end comparisons. And however, our method is not a budget-aware method. It's a quality-aware method. So there's maybe something to do better. Yeah.
Any other question? Okay, so I have 2 questions. One is that it seems like you use sample to compute the confidence interval for your answer.
Yes.
And the reliability of confidence interval often highly depends on the sample size. You always have to, for example, you want to use a central limit theorem, you have to be larger than 30.
Yes.
Then you can get a reliable confidence interval, which means for every comparison, you need at least 30 workers to give you answer, right?
Yes, you're right. This is our setting, actually.
So then, do you think it's a waste of the money?
Yes, you are right. But actually, in some applications, we don't need to pay money. For example, if we want to rank the hotels or rank the movies, the worker is free. You just need to implement this framework into the website and ask the workers, because currently the users often use the voting, right? Or rating a book, rating a movie. But actually this rate has some bias. We want to change this rating into a pairwise comparison. So if you have gone to 2 hotels, I want to know which one is better.
Yeah, but if you think cost is free, why don't you ask infinite number of crowd workers to do your task?
We don't want to trouble the worker too much. Yeah, we don't want to trouble the user too much. Yeah.
Okay. So the second question is, seem like you didn't provide a lot of details about your experiment settings. Would you mind saying something about, for example, what the crowdsourcing platform you use and how much you pay for the workers?
Okay. We pay 1 cent for 1 micro task, and we do the experiments on the Crowdflower platform. Yeah.
Okay, great. Let's thank the speaker. All right, so the second talk is about entity matching, which is my favorite topic that was done by Anhai. Very cool work. And the paper is about how you can use a very small amount of money to do entity resolution, maybe on millions of records. Okay, very exciting work. Let's look forward to this work. All right.
Thanks for the introduction. Good afternoon to everyone. My name is Paul, and I'm from University of Wisconsin-Madison, and I'm here to talk about our work on scaling up hands-off crowdsourced entity matching to build cloud services. This is a joint work with people from UW-Madison, Walmart Labs, and Johnson Controls. As you all know, a popular entity matching scenario is to find record pairs across 2 tables that refer to same real-world entity. For example, given 2 tables A and B containing personal information, we need to identify that the record pair here and the record pair here refers to the same real-world person. Entity matching has been studied extensively over the decades, and numerous solutions have been proposed. And current works have considered using crowdsourcing for the problem of entity matching. Now let me illustrate it with a quick example. Consider two tables A and B, with table A containing 3 tuples and table B containing 2 tuples. Typically, EM workflow begins by the user performing a blocking step where the goal is to remove obvious non-matching tuple pairs. To do so, a user typically writes heuristic rules such as do not remove all tuple pairs that disagree on the state attribute, and so on. So as you could see, after doing blocking, we have now reduced the number of tuple pairs to be considered from 6 to 4. Then the user would perform matching over these set of tuple pairs to predict each pair as a match or a non-match. At this point, traditional EM solutions would stop. Whereas recent works have considered using the crowd workers to verify the predicted matches in order to improve the matching accuracy. So in this example, if you could see, the pair CD is not outputted as a match because the crowd has not verified it as a match. As you can see, entity matching could benefit significantly from crowdsourcing. But current works suffer from a major limitation that they crowdsource only parts of the entity matching workflow. For example, if you look at the sample workflow here, we still need a user to perform the blocking and matching steps. This could be really time consuming. For example, the user may need to come up with good blocking rules. Similarly, when doing matching, the user may need to write rules, or if using supervised learning, the user may need to train a model. So to do so, he or she needs to create training data, tune the model, and so on and so forth. This also means that if we have a lot of such EM tasks, we cannot afford to associate a user for each such task. So to address these limitations, recently in SIGMOD 14, we proposed Corleon, which introduces the idea of hands-off crowdsourcing. So the key idea here is that Corleon crowdsources the entire EM workflow, requiring no developers at all. In particular, the user would begin by providing the two tables A and B as input, and Corleon would execute the workflow shown here. Specifically, it would first perform blocking over the two tables to obtain a set of candidate tuple pairs, over which it would perform matching to obtain a set of predicted matches. Then it would estimate the accuracy of those predicted matches, and if the accuracy is good enough, it would stop. Else, it would go back, find pairs which are difficult to match, and perform matching for those pairs again in an iterative process. Finally, if the accuracy reaches a good enough value, it would stop, and it would output a set of predicted matches and some accuracy estimates. So the key idea to note here is all these steps in this workflow is performed using crowdsourcing, eliminating the need for a developer at all. Though this looks highly promising, Corleon suffers from a major limitation that it does not scale to large tables, that is beyond 50K to 1 million tuples, as it executes mostly a single mission in-memory EM workflow. Let me illustrate it with an example. Hundreds of domain scientists at UW-Madison have entity matching needs. So to support such users, recently we were deploying EM services on the cloud, backed by our own in-house cluster of missions, and with the help of a few of our developers. So that when a domain scientist would come in and provide an EM task as input, our developer would assist the domain scientist to come up with an EM workflow, which would involve blocking and matching. And then that workflow would be executed on our cluster of missions, and we would return back the results. But this approach was not scalable as we started receiving more and more EM tasks because we had very few developers. So what we did was we decided to use the hands-off solution of Corleon in this setting, as it could eliminate the need for developers and it could perform matching using crowdsourcing. So now a domain scientist would come in, upload two tables, pay some money for crowdsourcing. Then we would internally use the yeah. Okay. So now a domain scientist would come in, provide the two tables, and pay some money for crowdsourcing. And we would internally use the hands-off solution of Corleon to do the matching using crowd workers, and then we would return back the results. And further, if the user doesn't want to use crowdsourcing, then the user could himself act as a crowd of one worker, leading to a self-service EM solution. As you could see, using Corleon for building EM cloud services looks highly promising. But the main limitation was it was very slow. For example, recently when we tried to match hundreds of thousands of tuples, it took weeks to match. which is simply unacceptable. So to address this, in this work, we scale the Corleone solution to tables of millions of tuples. Specifically, our solution is able to match tables of up to 2.5 million tuples for only $54 to $66 within 2 to 14 hours. And recently, our solution has also been deployed as a cloud service at cloudmatcher.io. At this point, it's not open for public, but you could see a demo of CloudMatcher in the poster session today evening. And further, we have also deployed CloudMatcher at various organizations, and currently it's used extensively at Johnson Controls, Marshfield Clinic, and various UW-Madison departments to perform entity matching. And in this work, we make 3 key technical contributions. First, we define basic operators and use them to model the entity matching workflow considered by Corleone as a DAG of operators. Second, we scale up these operators by developing efficient MapReduce-based implementations for those operators. And some of the operators are very challenging to scale, such as executing blocking rules over 2 tables, as we will see later on in the talk. Third, we optimize such DAG of operators by developing techniques that would optimize both within as well as across operators. So the key idea that we use here is to use the crowdsourcing time to mask the mission time. And further, we see that the ideas here could be potentially be applicable to other contexts, such as string matching, as well as scaling up any DAG of operator containing human operations as well as mission operations. Now, let me zoom into each of the 3 contributions. I'll begin by illustrating how we model the EM workflow of Corleone as a DAG of operators. So to recap, this is the workflow that we have seen of Corleone. In this work, we will only consider a part of the workflow involving just a blocker plus a matcher, as already this simple workflow is challenging to scale and covers most of the popular use cases. Now, let me zoom into the blocker part of the workflow. So in practice, there are different kinds of blocking used, such as rule-based, hash-based, sorted neighborhood, and so on. And hash-based blocking is very popular because it's easier to understand, highly scalable, and so on. But in practice, it doesn't work well for dirty data, as well as if the data has a lot of variations, resulting in very low recall. So Corleone uses rule-based blocking with rules such as these. For example, these blocking rules are used for blocking tables of books. So the first rule here states that if the Jaccard score over the book titles is less than 0.7, then drop the tuple pair. As you could see, such rules are more powerful and subsumes hash-based blocking. But it also makes it more difficult to learn such rules as well as execute these rules over 2 tables. Now let me show how Corleone learns such rules. So it begins by taking a small sample of tuple pairs from the Cartesian product of A and B. After taking a sample, it would train a random forest model over this sample using active learning. And during the active learning process, it would use the crowd workers to label the tuple pairs selected by the active learning algorithm. For example, a toy random forest with 2 trees is shown here. And after training such a random forest, we extract a candidate blocking rules from the random forest. So a blocking rule is a path in the decision tree from the root node to a leaf with a no label. For example, the first 2 rules are extracted from the first tree. For example, the first rule here is extracted from this path. So like this, we extract all the rules from the trees in the random forest, and then we use the crowd workers to evaluate the precision of these rules. So after this step, we basically have an estimation of precision for each of those rules. Then we try to select a subset of those rules and execute them over A and B. At this point, the blocking part of the workflow is complete. Now let me show how this workflow that we have just seen translates into a DAG. So we begin with 2 tables A and B as input, which is fed into the sample operator, which would take a sample of tuple pairs from A cross B, which is fed into the feature generation operator, which would convert each tuple pair in the sample into a feature vector. Then we pass the set of feature vectors to the active learn operator, which trains a random forest using crowdsourced active learning. Then we try to extract all the blocking rules from the random forest, then execute those rules using crowd workers, and then finally select a subset of rules, which is sent to the execute blocking rules operator, which takes the 2 tables as input and applies those rules to obtain a candidate set of tuple pairs to be sent to the matcher step. So as you could see, the workflow that we have just seen in the previous 2 slides is translated into a DAG. Similarly, we could model the entire EM workflow of blocking plus matching as such a DAG. In this case, we just need to append the DAG fragment corresponding to matching step. So for example, once we have the candidate set, we pass it to the feature generation operator, which basically generates features required for the matcher step. And so basically, again, we convert each tuple pair in the candidate set into a feature vector, which is then sent to an active learn operator again, which learns the final matcher to be applied. And then finally, we apply the matcher over the candidate set to obtain a set of predicted matches. At this point, we have represented the entire EM workflow as a DAG. And the DAG here contains 8 basic operators, which involve crowdsourcing. Some of them involve rules as well as machine learning-based operations. And we could compose a wide variety of EM workflows using such operators. And the key challenge now is to efficiently implement each of these operators. And some of them are very challenging to scale, such as the execute blocking rules here. In the interest of time, I'll just focus on the execute blocking rules operator, but you could find more details about all the operators in the paper. So the execute blocking rules operator would take in 2 tables and a set of rules and would apply them over A cross B and output a candidate set of tuple pairs satisfying those rules. So the rules would look like this, which we have just seen in the previous slides. So I've already explained the first rule. So the second rule here states that if the published years do not match and the absolute difference of the book prices is above 10, then drop the tuple pair. So if at least one of those rules is satisfied, we basically drop the tuple pair. And current solutions to apply such rules over 2 tables are very limited because they either treat the rules as black boxes, so they need to enumerate the whole Cartesian product, or they consider very simple rules such as single predicate conditions. Whereas our observation is that often these rules contain well-known similarity functions such as edit distance, Jacquard, and so on. So what we do is we exploit certain properties of these functions to build index-based filters and use those filters to avoid enumerating the Cartesian product. Now let me show what a filter is and then explain how our solution works. So let's consider the first blocking rule here that we have. So first, we convert this blocking rule into a positive rule by taking a complement of it. So now what this rule states is that if the Jacquard score of the book titles is at least 0.7, then keep the tuple pair. So now let me explain with a simple example. So let's say we have a string such as this, which has 3 tokens, that is 3 words in this case. So based on the definition of Jacquard measure, we could infer a size filter such as this, which states that for any other string to have a Jacquard score of at least 0.7 with this input string, the other string should have number of tokens in this range. So for example, if we have a string such as this, which has 3 tokens and falls within this range, then these 2 strings could potentially satisfy this predicate. But we still need to verify it by computing the Jacquard score. Whereas if we have a string such as this, which has just 2 words, that is 2 tokens, we could directly say that these 2 strings will not have a Jacquard score of at least 0.7 and drop those tuple pairs. So now let me show how we use those filters in our solution. So before beginning the example, I'll say that how we could apply such a filter over 2 tables. For example, such filters could be applied by building index over one of the tables. And for each tuple in the other table, we just need to probe those indexes to obtain a subset of tuples satisfying the filter. So let's see how our solution works. Let's take the same 2 blocking rules here. So the first step is to build indexes over one of the tables. So in this case, we will take table A. So we'll build 3 indexes, 1 for each predicate. And let's say we have built index I1 for the Jacquard predicate. And this could be an inverted index over the number of tokens. And let's say we have built I2 for the exact match predicate, which could be a hash-based index on the year attribute. And similarly, let's say we have built index I3 for the absolute difference, which could be a B-tree-based index. So after building these indexes, then for each tuple in table B, the naive approach would be to apply the rules over whole of A. But now we probe these indexes to locate a subset of A tuples satisfying individual predicates, then combine those sets to obtain the set C, which is the set of A tuples that could satisfy the rules for the current B tuple. So then we apply the rules to only those A tuples in this set C. As you could see, by using these index-based filters, we have avoided enumerating the whole Cartesian product. And we implement our solution in MapReduce framework. And the key challenge here is that often all these indexes do not fit into the memory of a mapper. So to address this, we developed multiple implementations which would balance the amount of memory required for a mapper versus the amount of work done in the reducers. And we use a rule-based optimizer that would pick one of those implementations. In the interest of time, I'll not go over these implementations, but you could find these details in the paper. Now let me briefly talk about the last contribution, which is about optimizing the EM DAG. So the key idea that we use here is to use the crowdsourcing time to mask the mission time. So intuitively, when a crowdsourcing operator is being executed, most of the time is spent on waiting for the crowd to answer. And during this time, the mission resources are idle. So what we do is we perform useful mission activities during this crowdsourcing time, such as building indexes, speculatively performing some tasks, and so on. So now let me show 3 such instances where we mask the mission time. So this is the DAG that we have seen before. So in this DAG, if you could look closely, we have 3 operators that perform crowdsourcing. The active learn operator here, the evaluate rules operator here, and the active learn operator here. So when each of this operator is performing crowdsourcing operation, during this time, we perform some useful mission activity. For example, in this active learn operator here, when it's waiting for the crowd, we build all those indexes needed to execute the blocking rules, so that when we reach this operator, we just reuse those indexes. Similarly, in this evaluate rules operator here, as you could see here, we already have the set of rules that could potentially be part of the final sequence. So what we do is we take these set of rules R, order them in the probability of being selected in the final sequence, and speculatively start executing these rules during the crowdsourcing time. So that when we reach this operator, we check if some of the rules are already executed. And if so, we just reuse those results. And finally, in this active learn operator, we do 2 kinds of masking. One is within the operator as well as across operator. So in this active learn operator here, there are 2 steps that are being executed iteratively. For example, it would select a set of examples to label, send them to the crowd for labeling. Then after getting the labels, it would again select the next set of examples to label and send them to the crowd, and repeats this process. So what we do is we mask this example selection time with the crowdsourcing time. Similarly, another optimization that we do is we speculatively execute the best matcher that we have over the candidate set, so that when we reach this apply matcher step, we have already applied the best matcher, we just need to return the results out. So the key idea here is that we use the crowdsourcing time to mask the mission time. So now moving to the evaluation, we extensively evaluate our solution over 3 real-world data with varying domains and sizes. And the data set size varies from up to 2.5K tuples to up to 2.5 million tuples. And we run Hadoop over 10-node cluster and these mechanical Turk settings. So the table here shows the overall performance of our solution. The column here denotes the F1 score. The column here shows the total cost in addition to the number of tuple pairs labeled. And this time here is the total time for the matching process. This is including both crowd time and mission time. And as you could see, our solution is able to match large tables with very high accuracy, low cost, and reasonable runtime. Also, note that Corleone used to take weeks to match such tables. Further, we also noticed that most of the time here is still spent on the crowdsourcing time, and we have significantly reduced the mission time. And coming back to the blocking step, the executing blocking rules operator took between 2 hours to 1 hour 13 minutes for blocking tables of millions of tuples. And our optimizations were very effective, reducing the total mission time by up to 70%. You could find more details and more experiments in the paper. We also tried to deploy Falcon in various real-world organizations to examine how it works in wild. For example, recently Falcon was used at Medical Center Marshfield Clinic for matching drug descriptions in 2 tables. So since the data was very sensitive, it was labeled by an in-house scientist, taking a crowd time of 1.5 hours and a mission time of 2 hours 10 minutes. And our optimizations were really effective, reducing the mission time to just 1 hour 6 minutes. And this also shows that there could be different kinds of workloads where even the mission time could be much higher than the crowdsourcing time when an in-house analyst is labeling the data. So this shows that why our optimizations of reducing mission time is very effective and required. So further, Falcon was also used by a team of economists at UW-Madison to match organizational information. And they did the matching using 2 ways, using crowdsourcing as well as using an in-house scientist. And in both approaches, they could achieve very high accuracy. And in the crowdsourcing mode, the cost was also very reasonable. And the interesting part to note here is that when the matching task was performed by an in-house economist, the total matching time for the end-to-end process was only over an hour. And before using our solution, they were actually hiring a real developer to do the matching for weeks, paying $15 an hour. This shows that how Falcon could be really effective and impactful in various real-world use cases. So there has been numerous amount of related work in this area, and we significantly improve each of the directions. In the interest of time, I'll not go over these, but you could find more details in the paper. And to conclude, we observe that Corleon solution is ideally suited for building EM cloud services, but the main limitation was that it was not able to scale to large tables. So in this work, we proposed Falcon, which scales the Corleon solution to tables of millions of tuples. And the key contribution here is to model the EM workflow as a DAG, scaling up each of the operators, as well as proposing optimization techniques that would use crowdsourcing time to mask mission time. And in future, we plan to explore newer optimizations, as well as consider more complex workflows. Also, we plan to make Cloud Matcher for public use very soon. And you could see a demo at the poster session. This concludes my talk. Thank you.
Questions?
So each rule contains a similar function, attributes, and thresholds, and any other. So I think which parts are you given for the rule, and which parts are learned? I don't think you only learn rules. You do not give any inputs.
I didn't get your question.
So I mean, all the similar functions, attributes, threshold, all of them are learned, or
yeah,
you give some input?
The entire rules. Basically, we try to learn a random forest. And
so you should give the similar function, I think.
Yeah, we give all the features and train a model, and then extract rules from the model.
I think functions, similar functions. How many do you use similar functions?
Okay. So we have certain rules on what kind of functions we use. For example, for long attributes, we use set-based measures for like Jacquard edit distance. But in overall, we use around 50 to 70 features for experiments.
So another suggestion is that there are many algorithms to apply the rules. For example, you mentioned that using set or using other features, many works on this problem, I think.
So the prior works for applying the rules, they either treat very simple conditions like just focus on one predicate like Jacquard greater than 0.5 or so on. There has been a lot of work on string similarity join literature. But very little has been done when we have a set of rules and efficiently applying those rules over large tables.
I think Jenna can give you some reference.
Okay.
Applying the rules.
Okay.
Any questions?
So I'm also interested in your, so first, thanks for your great presentation. And I'm also interested in how you will combine a set of rules together. It seems that each rule is just like a pruning function. That is, you will prune a lot of pairs of entities that will not match. So it sounds like each rule is kind of deterministic, that you will prune a lot of pairs that do not match. And my question is that probably this assumption is too strong, because if your rule is too aggressive, then you will have a low recall, and otherwise you have a low precision. So is it possible to assume that each rule is not deterministic. That is, basically each rule is a kind of classifier that you will given a pair and you will predict whether it's 1 or 0. And there are some reason works in data programming that assumes that each rule is a classifier, and this classifier has a different quality, maybe measured by precision or recall, and they will use some machine learning model, for example, logistic regression, to combine different rules together and predict whether a pair is just a good match or not. So yeah, this is my question.
That's a very good question. So we don't apply all the rules that we have extracted from the decision trees. So for example, if we have extracted the 100 rules, say, then we try to evaluate the precision of each of those rules. And then we try to select only a subset of highly precise rules. So what we do is for each of the rules, we try to estimate its precision, then coverage and selectivity parameters, and then try to select a set of rules that would have wide coverage. So for example, if 2 rules overlap too much, then we don't select those rules. So we do some simple heuristics there, but as you said, we would like to improve this approach of combining how we combine the rules. Thank you.
Questions?
So in your problem, you're just comparing tuples from 2 tables, right?
Yeah.
Now, some of us worked on the variation of trying to find all groupings of records that match. I presume that this could be adapted to that problem too, that variation.
Yeah, so
is that right?
One way to see it is after doing the matching, we could have a clustering phase where we could merge all the tuple pairs. So yeah, it could be adapted. And in future, we plan to do that too. Thank you.
Any questions?
So do you consider rule conditions? For example, a rule says matching, another say not matching?
No, we only extract the negative rules, right?
Only negative?
Yeah, because since we are doing blocking, so the intuition is we try to remove tuple pairs, right? So we extract all the negative rules.
Any questions? Okay. Oh, so it seems like this work tried to extend Corleone to big data.
Yeah.
And after listening to the talk, it gave me the feeling that you think the main challenge is machine time, not the crowdsourcing cost and crowd time, because you think active learning can scale crowd to big data. Do you think it's a valid assumption?
For example, if you look at our experiments with real-world users, where an in-house scientist is labeling the data, so in those kind of settings, the mission time is significantly higher than the labeling time. But whereas if you take experiments with the mechanical Turk kind of platforms, there the crowdsourcing time is dominant. That's what we are also observing. But what we see is that reducing the crowd time is also very important. And that is more an orthogonal work. And there has been a lot of work done in that area. So which could be basically included into this solution to reduce the crowd time.
Okay.
So ideally, we want to reduce both mission time as well as crowd time.
Okay.
This is just a first step, and we focus on mission time here.
I see. Okay. Another question is following on Guoliang's question. Because there's a lot of work on similarity drawings.
Yeah.
And it gives you a feeling that each rule have a bunch of similarity functions threshold, right? One naive way is you pick up a similarity function and the threshold and then find all the tuple pair that satisfy the threshold, and for the remaining one, you validate whether it satisfies the rule or not. Did you get a chance to compare some baseline rule execution methods?
So in the paper, we don't do any comparison because we couldn't find any related work that could be directly be comparable with the setting of applying complex rules. But yeah, if there is any interesting work, I'd like to know. Thank you.
Okay. All right. So let's thank the speaker again. So the next talk is from Stanford. The speaker is going to talk about question selection for crowdsourcing.
Colin, can you get close to
Mike.
Do you need the clicker?
No, I don't think so. I mean, if I click on here, it should work, right? Sweet. Whoops. All right, hi everyone. My name is Asif Khan, and I'm going to present some joint work I did with Hector Garcia Molina at Stanford on Crowd DQS, which is a dynamic question selection system for crowdsourcing systems. So the problem we're trying to solve with Crowd DQS is basically like the labeling problem. So given a set queue of multiple choice questions that you want answered by the crowd, how do you allocate a budget of B votes on these questions to maximize your accuracy? And this is like pretty common in crowdsourcing. Whenever you want to maybe generate like a training set for like machine learning, you might go to the crowd, or a lot of these sort of sophisticated crowd algorithms will have stages where there's like a batch of questions that are just a bunch of multiple choice things that need to be sent out. So this is sort of like the problem space that we're operating in. And it's a pretty simple problem to like specify, but it turns out sort of the standard approach that systems like Mechanical Turk offer you to work on this are fairly inefficient. So the standard approach is sort of this round robin approach where you allocate votes evenly amongst questions in queue and you aggregate your votes using majority voting. So that's also like fairly straightforward, but to give an example, let's say you have 50 questions and a budget of 250 votes, then you would allocate say like 5 votes per question. And as an example, let's say your questions are like yes or no questions, and you get 5 votes that are yes, 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 no, and no. So obviously you'll say, okay, maybe I should say the true answer for this question is a yes. But if you look at this, you can already start to see the problem. It's like after 3 yes votes, you already realize that the remaining 2 no votes would be sort of superfluous. So existing systems don't really let you easily stop at this point. So this is like one of the problems with the round robin approach. And there are a few other problems. So first, your votes are weighted equally. And there's a wide variety of skill levels in crowdsourcing platforms from the workers. And so it doesn't really make sense to give as much weight to someone who's a very accurate person versus an inaccurate worker. You also can't react to sort of spammers or low quality workers. So oftentimes, maybe some people have experience with this. They'll like put up a job on Mechanical Turk and then they realize that, 20% of their questions were answered by a spammer, and there's like totally useless data there. And so this is one of those things you can't really do anything about until the end of the job in the standard approach. Another thing is questions sort of get the same number of votes, regardless of the difficulty of the question or the previously observed votes, as we saw in that previous example. So there are usually a few types of techniques that people use to mitigate these types of problems. One technique is sort of, I would broadly classify as like post-processing techniques. So you may use like say expectation maximization, which I'll call EM in this talk. It was entity matching in the last talk, but so you can use EM to estimate worker accuracies and then reweight your votes based off of the observed worker accuracies. There's still some problems with this because you still have the problem of spammers coming in and like just destroying your budget. And your votes are still sort of inefficiently allocated amongst the questions. So another thing that people do is sort of like a not pre-processing, but happens before the job starts, where you might use gold standard questions, which are questions with labeled ground truth. I'll be calling them GSQs occasionally in this. But you use these basically to pre-screen workers. So you'll give a worker a set of questions, and assuming the worker passes all the questions or gets the questions right, then you allow them to continue working on the rest of your task. There's still some problems with this. Spammers can very easily game the gold standard questions if they know they're at the beginning of a task. You just do the first few questions correctly and then go to town afterward. It also really limits the pool of your interested workers. Once workers see that they need to do a test to answer or to work on your tasks, you get much fewer or much lower interest. And the more subtle thing, but it's really important to realize, is a significant fraction of your budget can end up being spent on testing. It sort of depends how long someone is going to work on your tasks. So if the average worker is only going to answer 5 to 10 questions for you, and you're spending 3 or 4 of these questions testing the worker, you're wasting a ton of your budget on these gold standard questions. And actually in the paper, there are some plots that we show where just asking gold standard questions up front is extremely wasteful, surprisingly wasteful. So our approach, which we call crowd DQS, which stands for crowd dynamic question selection, we basically built a system that's sort of on top of Mechanical Turk, where the user or the requester doesn't actually have to interact with Mechanical Turk at all. Instead, they have their questions and a budget which they specify to our crowd DQS server. And this server then takes care of everything else for you. So it'll post the questions to Amazon. And now when a crowd worker comes to Amazon, they don't actually get a question directly from Amazon. Amazon then pings our server and says, hey, this worker has come to request a question from your batch of tasks. What should we give them? And so now the crowd DQS server, in that instant, basically in sub-second or milliseconds, will decide what's the best question to show to this worker at that time and displays that to the worker. The worker submits their answer, which actually then goes straight to the crowd DQS server. And crowd DQS will then use that information to sort of choose what the best question is for future workers or for future instance or tasks in the batch. So all this is sort of hands off, and at the end of once the budget's been consumed, you'll have these set of predicted answers which then get sent back to the requester, and these answers will sort of have confidences in for all your predictions. So it takes out a lot of sort of the pain points, but to summarize, so crowd DQS, basically the main features are that we dynamically choose questions in real time. We efficiently learn worker skill level, and we do that through a combination of seeing correlated voting patterns and gold standard questions. But these are sort of randomly interspersed gold standard questions, so workers don't know where they are. We also actively block low quality workers as soon as we detect them. And I'll talk a little bit more about that later, how that happens. And then this is something that's, we've deployed live to thousands of workers on Amazon Mechanical Turk. And in some instances with difficult data sets, we've seen that this reduces labeling costs by up to 5 to 6x. So there are a lot of challenges in doing something like this. How do you estimate these worker accuracies in real time with limited evidence? How do you decide when to block workers? When do you choose to test a worker with gold standard questions versus learn more about their accuracy by seeing how their votes compare to other workers? And sort of what are the practical challenges involved? So to go over the strategy of going through this, I'll try to give mostly intuition about how everything works. To see the details, please see the paper. But we'll start out by talking about sort of at a very high level, how this question selection works. And so question selection is basically works in the following way. So a worker comes to request a question, and the crowd DQS server actually doesn't place any main or any instantiated questions on Amazon Mechanical Turk. We just sort of send these placeholder questions. So these placeholder questions are questions which just have a small piece of JavaScript. And this JavaScript then queries crowd DQS and says, hey, this worker has come here, what should I show him? And so the crowd DQS server will then look through all its its question bank and its bank of gold standard questions and try to estimate gain in expected accuracy for the predicted answers for each question if this worker were to then answer that question. And so how we calculate that is like, it's fairly straightforward for regular questions. For gold standard questions, it gets a little more complicated, so I'll talk about that in a little bit. But the key idea is that we're trying to estimate these gains in the predicted, or the gain in accuracy for the predicted answers that get sent at the end of the tasks. And this all happens like on the fly as soon as like a worker requests a task. So yeah, the gold standard question gain is where it gets kind of complicated, because gold standard questions are sort of one of two ways in which you estimate accuracy. You also can estimate accuracy, estimate accuracy through these like correlated voting patterns. So if you see like one worker's agreeing with all the other workers on a question, that's like a good indicator that this is like at least not a spammer, or is like a more accurate worker. And it turns out that you can actually learn a lot about a worker's accuracy just through seeing without asking any gold standard questions. So you need to actually have a good reason to ask a gold standard question. And usually this good reason should be, does asking a gold standard question now versus getting more useful votes from a worker lead to blocking the worker more quickly? And if the gold standard question leads to blocking a worker more quickly, how beneficial would that be? Because now the work that was being done by this worker is going to be done by some new unknown worker who may also be bad, may also be good. You have to somehow quantify how good is this new worker's work going to be, and put that into your computation. And finally, you also have to figure out, well, how many more votes will this guy contribute? Because if he's not going to do any more votes, there's no real point to ask him a gold standard question, because it doesn't matter what he does after that. So anyway, there are a lot of nuances there, so I just wanted to give a flavor for the trade-offs you have to consider. But for full details, please see the paper. Very quickly, I'm going to just kind of go over the worker model and vote aggregation. This is like fairly standard stuff. So for our worker model, we assume that the workers answer correctly with some probability P that we're trying to infer. And this is like specific to each worker that comes. And we assume in our modeling that each incorrect choice is equally probable with some probability 1 minus P divided by the number of remaining choices. And to aggregate the votes, it's basically an application of Bayes' rule. Don't worry about the equation so much. The important thing to realize is that we get sort of this most likely answer for each question and sort of a confidence that each predicted answer is correct. But it's dependent on knowing these accuracies of the workers. So how do we compute these accuracies? The typical approach is to use expectation maximization in these types of scenarios, or variants of that. And the problem with EM is actually when there's a few votes, there's a lot of noise in your estimates. And if you get a lot of noise in your estimates, then these confidences that you predict in your answers being correct are also very noisy. And it gets to be a point where you make bad decisions about like which workers to block, or you make bad decisions about where you should focus more effort or more votes. And so we wanted something that's a little bit more nuanced than sort of like the single sort of scalar worker accuracy that you get per worker through EM. And so we basically use something where the key idea is that we calculate a distribution instead of sort of a scalar for each worker. And so I think it's probably best to illustrate with an example. We consider like two different workers. So this first worker is someone, this is from like some of our experiments. He answered like 7 answers correctly and 4 incorrectly for a total of 11 questions. And now we have basically this likelihood distribution. So on the y-axis, we have likelihood, and on the x-axis, we have like the potential worker accuracy. And we're trying to basically see like what's the or the likelihood that the worker accuracy is, say, like 60% or 70%. So here you see it's sort of like a fat distribution because we don't have that much information about this worker yet. Now you can contrast this with like another worker, This is a guy who answered like 50 questions, which 43 were correct. And see here you see like, oh, he's got an estimated accuracy that's a little bit higher. The distribution is thinner. And it turns out that this ends up being sort of a more conservative way, especially when you have limited numbers of votes compared to EM in estimating worker accuracies. So we have like some plot in the, this is the math, you can leave that for reading the paper. But we have a plot basically where we're showing sort of on the y-axis sort of the root mean squared error of our worker accuracy estimates. This is in simulation because you need to have ground truth on worker accuracies. And then sort of like the average votes per worker that you see. And you see that they sort of converge to the same sort of amount, same sort of errors. But initially we have like much lower error, which is good for when you're trying to do this sort of dynamic question selection. The other nice thing about this worker accuracy estimation is it leads to a really intuitive way of doing blocking. So when should you block a worker? You should basically block a worker if you think that the replacement worker who comes in after that is going to be better than the worker you're blocking. So that basically means if we know the average accuracy of the workers in the pool, which you can learn through basically through the fact that you're calculating worker accuracies for everyone all the time. So let's say you know the average accuracy is 70% for your workers. Then all you need to do is say, what's the probability that this current worker that I'm looking at has an accuracy less than 70%, less than the average worker. So that probably means that the next worker who's going to come in is going to be better than this worker. And so like for this first worker, we would say, oh, this guy's got like a very high probability of being worse than average, and the next worker has pretty low probability of being worse than average. And then if it's a high probability, or greater than 50% basically, you can say, let's block this worker. And so we basically do that in crowd DQS. As soon as we see that like the distribution tells us that this guy's bad with like, I think we use 60% as our threshold. It's like 60% probability, then we block this person. So how does this all work in practice? So we tested this on a few different data sets. One sort of data sets of varying difficulty. So one, we had a cars data set. And I think in this data set, basically we had it was just a binary question where you ask, oh, what's the make and model of the above car? And they show a picture of a car. And to make it just slightly harder, we would make the choices be from the same make. So like if it's a BMW, you would only see BMW choices in the question answers. And we had another data set, which was a little bit harder, a dogs data set. I actually got some complaints. So the task here is to identify which of 3 closely related terrier breeds is being displayed in the data set, or in the image. And I actually got some, maybe not complaints, but I got some comments from professional dog breeders saying that this is actually very difficult to tell. So this is an interesting set, but there is like I knew what the right answers were. That was important for evaluation. And finally, I had like a sort of an easy data set just for testing things out, which was the sentiment data set where we had like product reviews and we were asked to say, ask workers to rate it as like either negative or positive. So it gives us sort of a range of difficulties to look at in our results. So in our results, we basically tested a baseline, which is basically round robin with majority voting, which is in blue, and then crowd DQS. And we saw like how many votes on average did it take to label the data sets perfectly. And so basically you see like for the cars data set, you have like the biggest gain. And this sort of because there's the distribution of workers is very bimodal. You have some people who are very good at labeling these cars, and we identify them very quickly. And the people who are bad or spammers, we block them very quickly. For dogs, it's a little bit different because you still see like a pretty big gain, but even for like the experts, it's sometimes difficult, so that the gains are less pronounced. For sentiment is interesting. We still see sort of like not as substantial a gain, but a not unnoticeable gain either. It's like 50% fewer questions. So in that case, even when the tasks are easy, it's still useful to be able to block sort of bad spammers and workers. I'm going to have to go, speed through this a little bit, but basically, you can sort of see what the breakdown is in where these gains come from. So green is just dynamic question selection only. B is with blocking, and then we also have gold standard questions. So you see, like each addition gives you more gains or fewer, or requires fewer votes. Finally, there's a couple of insights on like when gold standard questions are issued. We issue them to sort of these early prolific workers who basically ask a lot of, or answer a lot of questions, but we don't get any corroborating votes from them. And then also to these new workers who basically, when all questions have been resolved and all we need to know is more about the accuracy of the worker and not more answers from that worker. So I'll have to skip through this practical challenges. Please see the paper. It's a very interesting section on how you do this in practice. And finally, there's a bunch of related work on this. Some pretty interesting stuff on like how do you do this on Mechanical Turk and this like Kafka and iCrowd. And then this quiz is just on like an advertising platform. And then this optimistic knowledge gradient is very similar to sort of our some of our ideas on question selection. So in conclusion, CrowdDQS dynamically allocates votes to questions which need it most, quickly learns worker accuracies, and silently blocks spammers and low-quality workers. Determines when it's best to test a worker versus get more votes from a worker. And it's seamlessly deployed on Amazon Mechanical Turk to thousands of workers and can potentially reduce crowdsourcing costs and frictions significantly. Thanks. If you have any questions.
Okay.
Have you considered the consequences for workers of blocking them aggressively because they can get suspended?
I'm glad you asked
Amazon,
that question.
And you don't have a sort of necessarily perfect reason for blocking people.
Yes, so I'm very glad you asked that question because I wanted to talk about it but didn't have time. So if we go into our practical challenges slide, how do you block workers without pissing them off? And the answer is basically the workers don't know they've been blocked. Amazon doesn't know they've been blocked, but they've only been blocked from the perspective of CrowdDQS. So in practice, how this works is you can assign these things called qualifications. So you say, a worker must have this qualification to answer tasks from me. You can also, this is not used that often, but you can also do something where you say, a worker must not have this qualification to answer this task for me. So what ends up happening is, if we decide that a worker needs to be blocked, we assign them this qualification, which then prevents them from seeing any more of our tasks. But nothing actually happens to their worker rating. You don't get any angry emails saying like, oh, why'd you block me? And there is some discussion in the paper about like the nuances behind that. But thanks for asking.
Okay, I think we have time for one more question.
So thanks for your great presentation. So I have a question that given it sounds like other than a simple probability model worker, you also use a confidence interval that is to consider the number of questions that a worker has answered, to use this to model maybe distribution and to decide whether to block this worker. So do you consider this in marrying the task assignment? That is, when a worker comes, could you show us the basic idea of how to compute the expected quality of improvement of each task if the task will be assigned to the worker?
Yeah, so I mean, like the basic idea is, well, for gold standard question it's just hard to explain without just going through the math. For other questions, you can say, there's only like a finite, since these are all multiple choice questions, you can say, oh, well, what would my expected accuracy be if this worker answered this question this way? And then you can see basically how much does your expected accuracy increase for each question. It usually ends up being that sort of like the question that you have the lowest confidence in is the question that gets selected. Just because adding a new vote will increase your confidence in that question's predicted answer the most.
All right, so let's set the speaker here. So in the next talk, Cheng Liang is going to present a new crowdsourcing database system called CDB, built recently.
Here's good. Here's fine.
Good afternoon, everyone. I'm Cheng Liang from Tsinghua University, and I'd like to introduce our work CDB, optimizing queries with crowd-based selections and joins. Let me introduce the crowd-powered database firstly. The crowd-powered database can execute some queries which are hard for the traditional database. For example, consider we have two tables, one named professor and the other named paper. And if we want to execute this query on the two tables, we cannot get any result because the two columns, the strings between the two columns are totally different. However, if we execute the query on the crowd-powered database, then the UI designer of our database will generate some anti-resolution questions. And then after worker answering these questions, we can get the results. Then let's see the workflow of our system. Firstly, a requester submits her query using the CQL, which will be passed by the parser. The CQL is the query language we define. And then the graph-based query model builds a graph model based on the result. And then the query optimization generates an optimized query plan. And finally, the UI designer designs the interfaces and interacts with the crowdsourcing platform like AMT and Crowdflower. And finally, the worker answers these questions and the requester collects the results. Compared with existing systems, we have two main motivations. One is the optimization models. The existing works always adopts the traditional tree-based model to select an optimal order for a query. However, this method provides a coarse-grained optimization, which generates the same order for different joint tuples and limits the optimization potential that different joint tuples can be optimized by the different orders. So we propose a CDB, a graph-based model to provide a fine-grained optimization method. And the other is the optimizing goals. Existing works mainly focus on monetary cost. However, there are three multiple optimization goals in crowdsourcing. They are lower cost, higher quality, and lower latency respectively. So we provide a unified framework to achieve these multiple goals. Then let's see how to construct the graph. Given these four tables, we want to join them. And these highlight attributes are ready to be joined. There are three join practices in the example. Firstly, we consider such edges, the U2 and R1. you can see that they have very small similarity. So they have very small likelihood to be joined, to be matched. We do not consider such edges. So we just remove them. And we only keep such edges whose weights are bigger than a threshold, such as 0.3. So these edges are kept. And we get such graph. In this graph, each vertex in the graph corresponds to a record in the table. And for each join practice, there is an HE between the table T, the record T belonging to the table T, and the record T with superscript belonging to the table T with superscript with the weight bigger than a threshold. Then in the last slide, we construct a graph with a query with 3 join practice. But if we have a query with selection operations, we can also integrate the selection operation into the graph model. Considering this example, this query with a selection operation, we can generate a new table which contains only one attribute and one record, which is SIGMOD 16. And then we can use the new table, join with the table paper like this. The reason why we do this is because in traditional database, they always push down the selection operations and do them first. However, this may not be the optimal because, for example, if we ask this pair and the worker tells us it is a non-matching pair, then we can cost nothing for the selection operation. So we integrate the selection operation into our graph model. Then I'd like to introduce how we represent the answers in our graph model to help you better understand our model. We use the solid edges, the blue edges to present the matching pair, while we use the dotted edges to present the non-matching pairs. Obviously, a result, which is an answer, is a path with 3 solid edges. Unfortunately, in this example, there is no result because all the paths have a dotted edge. Then I'd like to compare the tuple level with the table level using the example. For a table level method, the table level method will determine a join order for a query. For example, the table method will ask the pairs between the first 2 tables. It will cost 9 questions. Since there is a non-matching pair, so these edges become invalid. We do not need to ask them. And then we can ask these 5 questions between the next 2 tables. And since there is a non-matching pair, so these 8 edges become invalid. And then there is only 1 edge left. So we ask them, and it is a non-matching pair, and these 8 edges become invalid. And so we ask the 15 questions in total. However, for tuple level, if we can identify these 3 red edges in advance, we ask them, and all these blue edges become invalid. So we only cost the 3 questions. Then let's see the differences with existing system. Our framework CDB supports most commonly used operations like collect, fill, selection, and join. And for optimization objectives, we achieve multi-goal optimization. And especially, we use techniques like truth inference and task assignment to keep high quality, which is better than the simple majority voting. And for the strategies, we use top-level method. And we support budget-based method. And finally, we deploy our system on cross markets like AMT and crowdflower. Here are the contributions. We propose a graph-based model and focus on multiple goals optimization. And we support many operations. And we deploy our system on cross markets. Then let's see how to control cost with known answers. Given a query with n-join practice, suppose G is the corresponding graph. A connected substructure of the graph with G with n-join practice is called a candidate, CDB query candidate, if it contains a corresponding age for each join practice in the query. For example, the U1, R1, P1, and C1 is a candidate. There are five candidates in the example. And a candidate is called an answer if all ages in the candidates are blue. For example, there is only one answer in this example. There are U2, it is U2, R2, P2, and C4. Obviously, the ages in the query answer have to be asked because their existence cannot be deduced by other color of ages. However, some red ages can make other ages invalid. For example, if we ask the R1 and P1, then and the worker tells us it is a non-matching pair. So the ages U1, R1, P1, C1, P1, C2, and P1, C3 are not needed to be asked. So there is a problem. Given the colors of every age, how to select the minimum number of ages to find all answers. To address this problem, we propose a min cut-based algorithm. And please refer to the paper for detail. In the example, the optimal ages are U2, R2, R2, P2, and P2, C4. It is a query answer. And then adding the ages R1, P1, and U1, R2, it is the optimal ages we need to ask. However, since we do not know the answers in advance, then we like to see how to control cost without known answers. And that is, we aim to select the fewer ages to find all answers with high probability. We consider a relaxation where we want to satisfy some random possible graphs with high probability. We use the sample method in the stochastic optimization. We can sample some possible graphs, such as these samples. And to generate a sample, we check each age E and set its color as blue with the probability weight E, and set the color as red with the probability 1 minus weight E. And there is a problem. Given S sample graphs, how to select the minimum number of ages to resolve all samples. For example, for graph B, the optimal ages are U1, R1, U2, R2, and R1, P1. And for each graph, we use the min cut algorithm we mentioned about to generate an optimal solution. And then we need to select the minimum number of ages to cover these sets, which is an NP-hard problem. And then we propose a greedy algorithm to solve this problem. That is, we compute the union set of these sets, and then we sort this set by the number of occurrence, and we act in this order. However, this method is expensive because we have to generate many samples, and for each sample, we have to run the min cut algorithm. So we propose an expectation-based method. Then for each age, we compute a pruning expectation, and according to its weight. This is a similarity score, and according to this weight and the numbers of ages connecting with it, and then the larger the expectation is, the larger number of invalid ages we can get after cutting this age. And then we also sort these ages by the expectation and act in this order. However, if one care about the latency, we cannot use this serial algorithm we mentioned above. Then let's see, then we should design the latency control method. Then we first consider the connected components. For example, these tuples in the different connected components can be accessed in parallel because they are non-conflict. So there are 6 different components in the example. Tuples in different components can be accessed in parallel. Then, as another step, we can consider edges containing tuples from the same table. For example, these are edges containing the tuples from the same table, table 1 and table 2. Because they are not concluded in the same candidate. And combining with the connect components method, we propose our latency control approach. Firstly, for each connect component, we select an ordered list by the expectation in descending order. And then we select the longest prefix in the ordered list that every 2 edges in the prefix are non-conflict. And at last, we ask all of edges in the longest prefix in different components. For example, for the second connected component, the longest prefix are these 2 edges. And this is the first batch we select to ask the workers. And we ask workers these questions, and the worker tell us the answer. And we prove some invalid edges. And then we select another batch of questions. And until all the edges are colored as blue or red. Then let's see how to control quality. The CDB control quality at 2 steps. One is called the truth inference. When our workers answer a task, we estimate the worker's quality and infer the truth based on the worker's answer and his quality. Let us denote W as a set of workers and T as a set of tasks, and the VT as the worker W provides answer A for the task T. And we can compute the probability of the S choice being true for the task. And we choose the choice with the highest probability to be the answer, to be the result of this question, to keep high quality. And this is a quality control method for the single choice problem. You can refer to the detail for other types of tasks. And the other problem is the task assignment. When workers come and request for a new task, we consider the worker's quality and assign tasks with the highest improvement to the worker. However, there are 2 main problems. One is we do not know the ground truth in advance. And the other is that we do not know how the worker can answer each task. So we can obtain despite the unknown ground truth, we can obtain the distribution of choice being true for each task. Obviously, the more consistent the distribution is, the higher quality will be achieved. So we use the entropy function to capture the consistency. So obviously, the lower the entropy is, the more consistent P is, and the higher quality will be achieved. And for the second problem, we do not know how the workers can answer the quality. So we can compute the S choice will be answered by worker W according to the worker quality and the distribution. And then we can estimate after worker answered the task T with S choice, we can estimate the distribution. And then we can compute the expected quality improvement for the task D assignment to worker W. And here are the task types we support. We support the single choice problem and multiple choices problem. And we also select the field problem, field question, and collection. Then let's see the experiment. We use 2 real data sets. One is called paper containing 4 tables, and the other is called award also containing 4 tables. and we use the AMT as our platform. And we also conduct our experiment on cross-market like AMT and Crowdflower. And we execute such queries on the two tables. And there are different kinds of queries, which include the two joins by selection, and so on. And let's see the cost. Compared with existing cross-source system and the anti-resolution method, we can see that we reduce at least 2 or 3 times cost because we use the top-level method. And then for quality, compared with other methods, we achieve higher quality by about 5% because we use techniques like truth inference and task assignment. And for latency, we also achieve lower latency than existing works because we use the latency control method. Here we come to the conclusion. We developed a cloud-powered database system with a top-level graph model. And we focus on optimizing multiple goals. And we deploy our system on cross markets. Thank you.
Any questions?
So when you talk about latency, you actually mean just the number of rounds or the number of questions you're gonna ask, or you do mean the actual time that a worker would take to answer a question? For example, a worker could take 5 minutes, the other worker could take 20 minutes, and you want to minimize that time. Which notion of latency?
Oh, you mean that some workers may spend 5 minutes and some workers may spend 20 minutes. However, we do not consider this question. We only consider the crowd iteration.
Okay. So the number of iterations that
the number of iterations.
Okay, got it. Thanks.
Any questions?
At the beginning of your talk, you talk about the graph-based and the tuple-based methods, right? So in your tuple-based method, actually you use some threshold to build up the graph. So how do you define the threshold?
Define what?
The threshold.
The
threshold of the edges.
The threshold. Yeah. There are many. You mean the pruning? The first prune some tuples which have small similarity. Yeah. In our experiment we set the similarity, the pruning, the threshold at 0.3. There are many works that this value, and we
but you know the value of it. Okay, it's sensitive to the size of your graph, right?
It's not so counts. Yeah, if you set the threshold too high, you may miss some correct results. But if you set it's too low, such as 0.1, you may remain lots of edges and the graph become too dense. It's time consuming. I think the 0.3 is a appropriate value.
So it's a trade-off between the precision and recall, right? And also the computation time.
Yeah. Pardon?
Okay. Okay.
The question is a trade-off between the precision recall and the computation time. Is it a question?
Yeah. That's the trade-off. We do not have the trade-off between about the threshold.
Okay. Any other question? Okay. All right. So we are just on time. Let's thank the speaker again.